This is task 2, question 3 from the Digital Electronics course notes. As in previous examples, I've started off with a standard first 3 columns of a truth table for a system in which we have 3 inputs. We can see from our diagram there's going to be 3 other values we need to calculate, the intermediate values D and E, and the output of our system Z. So we'll add columns to our table for these 3 values, which we're calculating in order to solve this problem. We always work from left to right in these diagrams because we sometimes need the outputs of earlier gates in order to find the final answer. In this case, we could choose to look at the OR gate fed by A and B or the NOT gate fed by C first. There's no particular reason to do one before the other. So just because of a letter value, I'll start with the gate that's got A and B going into it to give a value D. But in this problem, you could do it either way around. So let's isolate this gate first of all and think about what's going on here. Well, first of all, our inputs here are A and B. Indicated this on our truth table. Now, how an OR gate works is it will produce a 1 for the value D if A is 1, if B is 1, or A and B are both 1. The only time it won't produce a 1 as an output is if they're both 0. So as long as at least one of them is on, and that includes when they're both on, we'll get a 1 in column D. So if we look at the first row of the table, A0, B0, so we get a 0 for D, and same in the second row. But every other row, we've got 2 rows where B is 1, 2 rows where A is 1, and finally 2 rows where they're both 1. The condition is met that at least one of A or B is 1, and so we get the value 1 in the column D. So OR gates only give us a 0 if it's all zeros going into it. In every other case, as long as there's at least one in the input, we'll get 1 for our output. So that deals with column D. Let's have a look at the NOT gate. And it does matter to do this next. We can't deal with that AND gate until we have the values in column E. Well, this time what we've got is C as our input. So let's indicate this on our diagram. And this is important because sometimes when we're looking at a gate, we think we just look at the column before it, but D is not the input for this gate. D is, if we look at our diagram here, D is going to be, if I draw this line coming out of it, one of the inputs into the AND gate. So that's not what we're dealing with in our blue box here. C is our input. And as we've looked at in previous problems, what this tells us is in column E, write the opposite of column C. So a 0 goes in, a 1 comes out. So I'm just going to work my way through column C here and write the opposite value in column E each time. Instead of 0, 1, 0, 1, 0, 1, 0, 1, it's going to be 1 zeros repeating down the column. But that pattern repeats only because there's a pattern in column C. So each row I'm looking, saying, well, there's a 0, put a 1, there's a 1, put a 0. So our values for column E come from the opposite of the input C. Lastly, we have an AND gate to deal with. So I'll highlight this with green on the diagram. Our inputs are D and E, which is why we needed to do those other 2 gates first, because we needed these values in these columns in order to work out Z. Now, an AND gate will only give us a 1 in the Z column if both of the inputs are 1. So only when D and E are both 1 will we get a 1 for Z. So sometimes a quick way of filling in a table like this is to look down for all the rows in which we have 2 1s. So for example, here there's 2 1s, we put a 1 in the Z column. Here there's 2 1s, we put a 1 in the Z column. And here there's 2 1s, put a 1 in the Z column. And that means everywhere else is going to be a 0 because there's not 2 1s as input. An AND gate requires all inputs, in this case, both of them, that means, to be 1. So that's how we get our outputs for column Z. And that completes task 2, question 3.